So we are live with the lightning talks. We are going to start with two presentations by Simon. Go ahead.
Yeah, hi, I'm Simon Sora. And James Jones is here as well, I think.
Yep, hi.
So we had a workshop about allocation constraints yesterday, and this is a summary of the discussions we had back then. We wanted to make sure that our high-level design was fine. So we are pleased to see that there was no objections to the high-level design. And the idea to have a common function to merge constraints was fine too. The fact that we use one constraint set per modifier seemed like it would work fine with current hardware. We were wondering if vendor constraints would be necessary. So a little bit like modifiers, where you have a file with a registry of vendor constraints. So it seems like we don't need them now. But anyways, if we end up needing them, it's possible to extend the current design to support them. So that should be no issue. We also talked about the fact that constraint sets have a serialized form. So that makes it so we can send them over the wire over Wayland or X11. So that's good. We talked for a bit about the EGL API. Because we need some kind of flag to say to EGL whether we'll use a buffer for texturing or for rendering. And it seemed like external only would be good enough of a proxy for that. We talked for a bit about allocators. For now, we target only GBM and Vulkan in our proposal. But it's not a good fit for things like camera and encoding, video encoding. There's no solution to this yet, but we noted that our design should work fine with new allocators anyway, because you can just extend the allocator API to take a constraint set. So it should work fine once we have something else, for instance. We asked about possible trickery hardware limitations that would need to be encoded into constraints. There were some examples like buffer objects planes with each plane in a different bank, and shadow buffer blitz necessary between layout transitions and Vivante. Yeah, we'll keep those in mind. I think it should work. We talked also about storing extra metadata in some pixels. So this is not fully solved by constraints. I think it was a question from ARM. It's not fully solved by constraints, but constraints help. But yeah, there are some things which are outside of the scope of constraints, which need something else. We ask also what should be the home for the merging library. So our current solution is to use a UAPI header. Some issues with that is that everything is public, so we can't have internal helpers or internal structures. And also, all of the logic is inline downstream in compositors and all users. So if we want to add a new constraint, we need to recompile all of this downstream usage. So that's not great. Another solution is to use VDSO, but we need to justify inclusion in the kernel. So we need to, we can't just put anything in the VDSO. It's not yet clear if we would have a case, a good enough case to make it. the kernel definitely needs to produce constraints for KMS, for instance. But maybe the merging constraints could be useful too. Yeah, we're not sure yet. Another solution is to use to put the merging library in a shared user space library synced from the kernel. It's pretty small, so it could maybe be part of libdrm, and it seems like this idea was pretty well received. So maybe we'll go with that going forward. James, do you want to continue?
Sure. So there was a question about how we handle things like a constraint that dictates whether memory should be accessed, cached, or uncached from the CPU, and how we would expose that. Would that be a property of a particular heap of memory, or would it be something expressed separately? The answer isn't totally clear right now, but one thing we talked about is that if it was a separate constraint, it might make sense to expose that from the mapping APIs themselves rather than trying to return it from, say, KMS. So like if you asked GBM for a buffer that you could map, you could return new constraints that say, it should be cached or uncached or something. It was clear that the heap ID proposal is, a work in progress. Heap IDs themselves are a rather large problem space. So there's discussion about how we should solve that. Should we make everything go through the DMA above heap API to get a heap ID? Should there be the namespaces like we proposed? So we need to build up the use cases there. Find the killer use case, and maybe start out with just a local unshareable, meaning like your video memory, and a non-local shareable, meaning the rest of system memory and everything that everyone can talk to. And find a way to expose these and discover them through some programmatic means, both within the kernel probably and for user space apps that want to allocate from them. So there's some open items still. So there's more concrete proposals to come on some of these things. The next action was going to be that I'm going to start an email chain with the people at the workshop and others we nominated that were probably interested, mostly people from the DMA above heap community. If anyone has ideas and suggestions or wants to track things, we decided to use the GitLab page for the current DRM constraints and prototype library as a place to file issues and track the development for now. And that might evolve over time, but that's the current link. I have one more slide here with the shameless plug. I still haven't checked in the code from my presentation last year about adding format modifiers to, or more detailed format modifiers to Nouveau. So if you have time, please review these merge requests. One just reworks the way we handle auxiliary planes in Gallium to make it so that the auxiliary plane data is actually local to the drivers that use it. And the other one adds the more detailed format modifier stuff that I presented last year to the Mesa Nouveau Gallium driver. And this is blocking some of the more interesting stuff that I presented last year, like format modifier transitions and enabling compression for more formats in Nouveau. So take a look at those, and then we can move on to the constraint stuff.
Yes, thank you for participating in the workshop. That was pretty constructive, I think.
So second presentation from Simon today.
Yeah. Hi again. I'm Simon Sir. And I'll talk about wlroots, the future steps for wlroots. So just for people who don't know yet, wlroots is a Wayland compositor library. So you can use it to build a compositor. It contains a set of pluggable, composable, and opinionated modules. So basically, you can start with using all of wlroots, and then you can start thinking that you need some more custom stuff for instance, rendering, and you can throw away the wlroots renderer to do something else. You can customize basically everything. So it's been used, for instance, by game scope to do pretty crazy stuff and completely removes our backends. This is completely fine, and this is not a hack at all. It works pretty well. So it's about 50,000 lines of code you are going to write anyway at the beginning, and then you can customize stuff. So what does the wlroots architecture looks like? So you have some compositor code here in blue that is not part of the wlroots, and then some other wlroots modules can be used by the compositor. So for instance, backends, the compositor can use ready-made libinput and DRM backends to get input events and display things on screen. And you also have other backends such as Wayland, X11 headless. And the compositor also needs to talk to Wayland clients. So wlroots contains some protocol interface implementations. So for instance, WL compositor. There are also some other implementations such as WL SHM, which allows clients to push buffers to compositors, to share buffers with compositors. Linux DMA for GPU buffers. And we also have some protocol extensions to allow clients to capture the contents of the screen. That's what I am using right now, by the way. So with all of this, the compositor can get buffers from client and can display stuff, but it also needs to render stuff. So we have some rendering code to help with that. So how does that integrate with the existing graphics API? So we're using EGL and OpenGL right now. So I'd say the first step is that backends create an EGL display and an EGL surface. This is backend specific. You don't create it the same way on DRM and on Wayland. So the backends need to do this, and then the backend gives it to the renderer. It's because the renderer needs the EGL context. The compositor can then call functions such as EGL make current, EGL swap buffers, and everything like this to control when to push frames to the backends and display them. Protocol implementations such as SHM need to upload textures to the GPU. Linux DMA need to import textures to the GPU. And then the compositor can talk to the renderer and ask the renderer to perform some GL calls to draw things on screen. The screen copy implementation can download or export some render buffers and give them out to the clients. There's some more hairy stuff going on with the DRM backend. Because we need some special rendering code for the cursor, which only accepts certain sizes in some cases and some certain formats. We also need some rendering code to perform multi-GPU, to bleed images basically between GPUs. So yeah, some more EGL bits there. And we have some pretty complicated stuff going on for cursors, because the clients can set the cursor, and we need to share this cursor with the DRM backend, so texture gets transferred somehow. Yeah, it's pretty messy, and that was only the easy part, because we want to implement a lot of other features. So one of these features, zero copy presentation, also known as direct scan out. We want to do that with multiple planes. We want to implement explicit synchronization. We want to implement multiple renderers, for instance, Vulkan and Pixman. We want to implement zero copy screen capture. We want to implement being able to use headless and DRM backends at the same time. So all of this makes the current architecture pretty complicated. And some of these features are not really, yeah, it's pretty hard to support them. Some of the features are already implemented, by the way, but not all of them. So we could choose to abstract away all the EGL things to be able to use Vulkan and things like this, and try to glue everything together in under a single interface. But that would be a lot of work and pretty complicated. So Scott understands that idea to completely throw away all the EGL things. That means stop using EGL surface and only care about abstracting a single thing, which is buffers. So we've introduced a WLR buffer abstraction, and we can basically use it everywhere. That's pretty cool. We've added a new allocator, which can allocate from JVM and gives out buffers to the compositor. The protocol implementations can give buffers coming from client to the compositor. The renderer can import all of these and texture from render to the buffers. All the backends can accept buffers, and the screen copy can grab buffers. So we only talk with buffers. That's the plan. It's still work in progress, but we'll get there eventually. That allows us to simplify a lot the internal architecture. That's it. Thanks for listening.
Yeah, thank you, Simon. And we are now going to switch to Roman, who is sharing. So, Roman, are you ready?
Hello, yes, can you hear me?
Yeah, we can hear you, and right. Your slides are on, so you can start.
Great. I will quickly introduce a small project I was working on in the last month, mainly, and before it as well. It's called Disman, and it's the tagline is Universal Display Management. You can see here a UI application making use of Disman. Disman is primarily aimed at managing multi-display setups. The motivation for that is that these multi-display setups are pretty common, and the configuration of multi-display setup or even a single display can be complex. And normally a user wants the configuration to be remembered for the next time the session restarts and so on. There are also different windowing systems and compositors in the Wayland windowing system, which have different interfaces. For example, on X11, render is used, and on Wayland, we have a multitude of different interfaces for display management. The first one, I won't read all of them, but the first one is by wlroots. The second one is by QuinFT. Then KDE has also a separate output management protocol, and other compositors like, for example, Matter use dbus. So coming to Disman, what exactly is this thing? It's first and foremost a library for front-end creation. So that's probably the most interesting part for the community. So you can use it to write a UI for display management. It's for the client, it's only required to use C++11. And at the moment, there is still some Qt in the AP surface, but my goal is to remove this over time. Use CMake, and I also want to commit to Semver, but at the moment, there's not yet a stable release. Disman, on the front end, it has this library. On the back end, there are several plugins that can be loaded at runtime depending on which windowing system is used and what compositor is detected. So these backend plugins can be loaded either in process by the client, making use of the library Disman, or they can be loaded out of process via a dbus service. The dbus service has automatic activation, so it's called once in the session, and then it's running continuously until the session stops. So this can be done, for example, with Disman CTL, Disman Control, which is a command line tool, and you can just issue, for example, Disman CTL -W, and then it watches continuously all changes, and the dbus service is started, which then loads configurations and talks to the windowing system. Coming to a quick overview in this table. So we have at the top, we have clients which want to make use of Disman for display management, and they would either talk directly to the backend via an environment variable. This is the leftmost direct client, or they can use the dbus service and then talk via dbus to this service, which then has already loaded some windowing system plugin, and it has also some file control, which saves the configuration of the outputs and the overall setup to some files on disk in the user directory. So that's directly one of the features. So it saves and loads the display data. It can do this per combination of displays. So it identifies a display. It normally does this via the display manufacturer and the model and the serial number, and also via the connector it is connected to. That's because displays can have different properties depending on which connector they are connected to. For example, on DisplayPort, maybe they have a higher resolution or refresh rate than on HDMI. So you can do this per combination of display, or you can do this globally for a display. So when you change the scale of your display, for example, once to 2, then it will be remembered in all future setups. So you don't have to reapply it all the time. But you can still override it for specific combinations. For example, if you have a laptop with a high DPI and at work you use it with a keyboard, it's further away, then you can, for this specific combination with an external display, then most often you can use, you can set a specific scale factor, which is only applied when. It generates optimal configuration. If you connect a new output, it has an automatic selection of resolution and refresh rate, or you can manually override it. You can also do display replication, or it's often called mirroring. And it has laptop lid detection via UPower and lock-and-D. So if you close the lid and an external monitor is connected, it will disable the laptop display. So that was Disman. K-Display, that's a fork of K-Screen, the KDE utility for that. And it previously it had all the logic in it, so that's what I did last month. I basically removed all the logic from K-Display and implemented it in Disman, most of it. So it's basically gutted now in just a UI application, but it's a good example of how you can make use of Disman. It has an independent graphical app for changing the display settings, and it also has a plasmoid for the KDE workspace, so you can quickly change it from your taskbar. And of course, it makes use of a Disman library. Yeah, you can see it here. It has automatic resolution, refresh rate, and so on currently enabled. And you can change various parameters of your displays. So future plans is maybe support for docking of laptops. I would like to add a GNOME Matter Wayland backend plugin, which then talks to the dbus interface of GNOME Matter. I want to stabilize the implementation and clean up the library AP. I want in this I want to remove the Qt dependencies from Disman as much as possible. At least it shouldn't be part of the library API. And at some point, I want to release a stable release 1.0. Next week, I plan to release a beta for the next unstable release at least. So project organization, you can see here the URLs of the project homes. You can send in merge requests. They are built automatically and auto-tested on CI, and the releases are aligned with KDE Plasma. As said, next week beta release, then with the next KDE Plasma release, the next unstable release. And the development is open via GitLab issues. Check it out. You're welcome to try it out. Thank you.
Thank you very much for your presentation, Roman. And now we are going to switch for the last presentation of the day before the closing session, which is by Bas. Okay, Bas, you're on.
Hi all, I'm going to talk about an update for AMD DRM modifiers and why modifiers. So basically the thing why I want to have modifiers on AMD hardware is that it's very important for image imports of Vulkan. Like the Vulkan, normal Vulkan extensions only really do Vulkan to Vulkan. So if you want to import something that wasn't created by Vulkan, you'll have a problem unless you use modifiers. And that's essential for things like compositors using Vulkan. Like Gamescope can currently do it, but it has pretty much driver-specific hacks to make this somewhat work. It's also relevant for zero copy video playing, like when you want to import a buffer from the decoder. It helps with compression for non-full screen windows, like when, for example, the display unit can't use compression, but rendering can and texturing can, then you can use for non-full screen windows. And the other feedback I got was that for overlay and underlay planes in compositors are often uncertain whether they can use an extra plane, because with modifiers it's not always possible to scan out on an extra plane. So that's kind of use cases where you can use modifiers to enable that. And the basic thing a modifier is just a 64-bit int that says like, hey, this is the kind of texture layout I'm going to use for this image, and we kind of want that to be an injection. And typically on AMD hardware we use like 3 texture layouts. So trivial implementation. We define linear, we define displayable, and we define non-displayable, and we're done, right? Well, not quite that far, because there's GPU and driver differences. Like AMD tends to change their texture layouts like every new chip, one way or another, and often between chips in the same generation as well. And then there's some data that is driver only and it's in the texture memory. So if we update the driver, we would have to change that. So for the GPU differences, like there's some options here, like you can add the chip ID as a parameter to the modifier, but then like chips with the same texture layout will result in duplicate modifiers. Like if chip A and chip B have the same texture layouts and we use 2 parameters, then all the drivers in the kernel and user space would need to have the same logic to figure out like, hey, these are really the same modifiers. We need to expose either neither or both of them or something like that. So that gets quite complicated quickly. Another option would be to add parameters to completely identify texture layout, and that's what I've mostly gone with, but it gets quite detailed and complicated because there's really a lot of options depending on the hardware how this changes. So yeah, I tried to send an RFC like 1+ years ago, and that's got a bunch of pushback. Like the total modifier info was about 40 bits out of the 64. And some people also questioned my source data on which parameters are actually relevant for the texture layout. And that took me back quite a bit, especially because as third-party hobbyist developer, it's kind of hard to exhaustively go and test all hardware to make sure that the texturing library you used really corresponds to literally every hardware out there. So I kind of let it sit for a while, and now I'm back with a new approach. I'm doing only newer GPUs for now, partly because there's a clean break in texture layouts. Like it's much simpler now, which means I can iterate quickly. It has more interesting things we can do with compression, so it's actually more useful than for the old hardware. And I have an almost complete hardware collection to test, so I can actually resolve the pushback. And I have so the status is pretty much that I have it working with GL and the kernel, and I have some older revision working with Vulkan, which I still need to publish. The GL support is in pretty good state. Kernel, it works and is tested, but could definitely use more feedback. And then on the to-do list, I would like to publish the Vulkan support. I would like to add IDT test, because there's almost no automated testing for display side of things at this point. And I would like to add the names to DRM info as a quality of life thing. And I have a personal repo with some issues, and if you have ideas or concerns, feel free to add it to this central location. Thank you all.
Okay, thank you, Bas. That was the last presentation of the day. And now on to the closing session.